Hello guys, welcome to Yebo Physics on a Thursday afternoon, and I hope I find you well. We're going to be looking at questions on static equilibrium. That is chapter 14. That is chapter 14 on the questions on the FVV 101 physics workbook, or if you're following for the PHYV 101 group, that will be tutorial 6. So we're going to be solving problems together. If you're joining in on Teams, please feel free to unmute your mic and share with us. If you are joining live on the YouTube channel, feel free to type your question or contribution. I should be able to see it and we can be able to interact. So we're going to start with solving problems that are on the physics workbook, and the concept is similar whether you're doing FVV 101 or you're doing PHYV 101. The concepts or the concept is similar in solving these problems. So these problems that we're going to do will benefit both groups. So I believe that you have attempted these questions prior, and hopefully if you had any challenges in solving any of the problems, we should be able to discuss those together and be able to comprehend how we're supposed to go about some of the problems. So let's start with question 2. It reads, suppose a horse leans against a wall as shown in the figure below. Calculate the force exerted on the wall, assuming that the force is horizontal, while using the data in the schematic representation of the situation. Note that the force exerted on the wall is equal and it's equal in magnitude and opposite in direction to the force exerted on the horse, keeping it in equilibrium. The total mass of the horse and the rider is 500 kilograms. So we are being requested to calculate the force exerted on the wall. All right, so remember, the first thing that you have to do is to identify the forces that are acting on the system, right? Identify the forces acting on the system. So we have got our F on the wall, which is equal and opposite to the force that the horse exerts on the wall. There it is. And the other force that we have is the weight W, which is going downwards. Okay. Right, so we have to pick a point which is going to be our pivot, and then we take moments about that particular point that we would have chosen. All right, so I prefer to take moments about this point, about the okay. So that will be our pivot or reference in solving this problem. And we should remember when taking moments that the sum of moments or the torque should be equal to 0 for a system in equilibrium. And we're told that this system or situation, it's in equilibrium. All right, and we should also remember that is equals to our f sine theta. So this is just a reminder as we are starting. Okay, so then what do we do now that we have identified the forces that we have? We've chosen the pivot. And now we should remember that we are looking at the distance to the pivot, which is our R. So if you consider the weight W, or the weight W, and if we're considering this point as our pivot, the weight W, if it continues downwards, it will tend to move this system in a anti-clockwise. I'm sure you can see that. All right, and anti-clockwise torque will be positive. And if we look at this force W, it will move in this direction, or this torque, it will move in this direction, which will be clockwise. Therefore, it will be positive. All right. Now, when we look closely, the angle between the line of action, and the distance for FW, theta is 90 degrees. And in this case, again here, our force line of action and the distance to the pivot, the theta angle is 90 degrees. All right. And we know that sine of 90 will give us 1. So if we've done this, we have already half solved the problem. Okay. So let's sum a moment. So that is going to be F, the force that we're looking for, which is positive, F. Okay, that distance will be what? Okay, we can just say R W F W sine theta. Oh, I should change something there. We said the clockwise is negative, not positive. Clockwise is negative. The anti-clockwise is positive. So this should be negative, then plus the weight. So I'll just say this is RW. Okay. Which is equals to 0. You can then equate this. You find that this will be your RWFW sine of theta equals to RW sine of theta. And we say the angles are 90, so this goes, that goes. All right. And your R to the wall, which is this distance, will be 1.2. So this becomes 1.2 times the force F that we're looking for, which is equals to the perpendicular distance there, 0.35, and W, which is the weight, and we're told that the mass of the horse and the rider, it's 500 kilograms times 9.8 or 9.80. Then our F will now be equal to 0.35 500 times 9.81 all over 1.2. Now what remains is for you to punch. So let's punch that together. So we get 1430, okay, newtons, which is what we expected to get from the answer that is in the workbook. So basically that is how we've worked that problem out. Now this question continues, it doesn't end there. It says calculate the magnitude and direction of the force calculate the magnitude and the direction of the force on each foot of the horse who are on the ground, assuming the center of mass of the horse is midway between the feet. The total mass of the horse and the rider is that. What is the minimum coefficient of friction between the hooves and the ground? Note that the force exerted by the wall is horizontal. Right, so the force exerted by the wall is this force F exerted by the wall, okay? So to balance that force, there's going to be a frictional force in this direction, all right? And this will be our frictional force, okay? And you should remember that for a system in equilibrium, the sum of forces in the x direction should add up to 0. And in this case, we only have got two forces. The other one is in the positive direction and the other one is in the negative direction. So realize that it will be Fw minus Fr equals to 0. So which means Fw is equals to Fr, which means our frictional force is equals to our frictional force is equals to the value that we calculated there, which is 1430 newtons. Why do we need the frictional force? Remember, to calculate the coefficient of friction, F is equals to mu R, where R is the reaction, right? And we have the reaction from that point going up, okay? That is our R, right? And having said that, again, the sum of forces in the y should add up to a 0. And if you look at the forces that we have got a reactional force in the positive direction, and we have got the weight in the negative direction, which is pointing downwards, which means the reactional force is equals to the weight, and which means the reactional force is equals to 500 times 9.81. That would be the what? The reactional force. All right. So now let's find the coefficient of friction. Mu is equals to F over R. So that becomes what? Force, which is the frictional force. We said it's 1430 newtons over the reactional force, which is 500 times 9.81. So we punch that. We get 0.292. If you round off, yes. So I see this is actually part B. Part A, let's keep part B. What was part A saying? Calculate the magnitude of, okay. So basically now you have your frictional force acting there, and you've got your reactional force acting at that point, which means we're going to have a resultant force there, which is what we are being asked to calculate on part A. Apologies, I skipped that by mistake. So basically we are actually looking for the magnitude. So F becomes equals to the square root of F in the X, it's what? F in the X, it's 1430. Then F in the Y, this is 500 times 9.81 whole squared. Then we punch that. So you should remember this when you're looking at your vectors. Okay, so this is 5,109 newtons, and this is for okay, so they said we should calculate for force on each foot, so this will be for both, right? So which means there will be F over 2, which is equal, so we divide that by 2, 5,109 newtons over 2. So if you say that divided by 2, you get 2,554 newtons, which is what we are expected to get there. So that is what we're expected to get. All right, so now that you've done that, you can now calculate the angle. You should still remember that your angle theta will be equals to arctan F in the over F in the X, right? I'll not compute this. This you should still remember from your vectors, right? Remember in the first chapters, we looked at vectors and we were looking at resolving. So you should try this out and satisfy yourself that you get the expected answer that is here. All right. So I hope that you try that out. Okay, so basically that is how we're supposed to work out this problem. Those who are joining on Teams, if you've got any questions, please unmute your mics and share. If you are following, if you've got a contribution, please also type. If you're following on YouTube, you can type your comment. We should be able to see it and we should be able to discuss it here. Otherwise, we will proceed to the next question. That is question 3. It's actually question 4. We just finished question 3. Right, so we have another interesting question that we have here. So the question reads, suppose the weight of the drawbridge in Fig 9.3 is supported entirely by its hinges and the opposite shore, okay, so that its cables are slack. The mass of the bridge is 2,500 kilograms. A, what fraction of the weight is supported by the opposite shore if the point of support is directly beneath the cable attachments? What is the direction and magnitude of the force of the hinges exerted on the bridge under these circumstances? So we are also given the answers, so we can work towards that. Right, so what do we do? What do we start with there? We will obviously start with putting a sketch, right? Putting a sketch. So that is our beam. We're going to put the weight, which is somewhere here. And we have the reaction force here. Reaction force on the opposite side, which is the shore side. And this is where we've got our hinge. Okay. And we can label and say this is a F on the hinge, and this is F on the shore, and this is the weight W. So all this is what we are given in the question. We can also label this is 7.5 meters and this is 1.5. What else? What else? What else? What else? Basically, that is it that we're given in this particular question, basically. So we can then take it from there to look at the sketch and then solve the problem that we have. So let's understand the question. What fraction of the weight is supported by the opposite shore? Okay. So what are we looking for? What are we looking for? What are we looking for? And the other thing that we should remind ourselves is we should recall that for a system to be in equilibrium, the resultant torque is 0. Okay, the resultant torque is 0. So we can then choose to take moments about the hinge. You can choose to take moments about the hinge. Okay, and take moments about the hinge. Why? So that we eliminate this unknown force and we remain with what we're being asked to find. Okay, so I realize that the internet connection is not stable, so those who are following on YouTube, you might experience some delay. You might experience some delay in the broadcast, but however, we'll proceed. So like I said, a resultant torque, or the sum, should add up to 0. Why? Because the system is said to be in equilibrium. All right, and we're eliminating the force at the hinge, because we're taking moments at that point. The distance will be 0, so therefore it is eliminated. So the turning effect due to the weight, or the torque due to the weight, it's going to be clockwise, therefore it's going to be negative, whilst the turning effect, or the torque due to the force on the shore, it is going to be anti-clockwise, therefore it's going to be, the torque would be positive. All right, so torque due to the shore is positive, minus the torque due to the weight should add up to 0. Then we can now take the moment. How do we go about that? So it's just a similar concept. RS F S sine of theta minus, we can say RW times FW sine theta equals to 0. But we realize that the angles is close to 90 degrees, therefore sine 90 will give us 1, so all this will go, right? So which means we'll remain with RSFS equals to RWFW, and we are actually looking for the fraction. Okay, so it's fraction, then we're looking for FS, fraction of the weight, which is supported by the opposite shore, right? So what that implies is we can then make force due to the shore over the weight, because we're looking for the fraction due to the weight. So it's going to be Fs that will be Fs over Fw equals to Rw over Rs. So that is the fraction that we're looking for, and Rw it's 1,5. To that point where we've got Fs, that's 1.5 plus 7.5. So we can then punch this to get our fraction. Punch that. Okay, so it's 1 over 6. So all right, so which is 1/6 of the weight, which means this point supports 1/6 of the weight, and which means that the hinge supports 5/6 of the weight is supported by the what? By the hinge. Okay, this is going to be useful in the next part of the question. Okay, so that is how we go about that part of the problem. Now moving on to part B, Part B says, what is the direction and the magnitude of the force the hinges exert on the bridge under these circumstances? Okay, so that is what the next part of the question is looking for. So what is the direction and the magnitude of the force the hinges exert on the bridge? So we have already identified that if the shore side is supporting the bridge by exerting a force of 1/6 of the weight, which means that the hinges are exerting 5/6, and the direction is upwards. So it's going to be 5/6. FH is going to be 5/6 of the weight, which is equals to 5/6 times what was the weight? 2500. 2500 times 9.8. Then you have to punch that. We have to punch that. So we get 20,416 newtons. So if you put in standard form, this is what you get. If you express your answer in standard form, that is what you would get. All right, so that is what you're supposed to do, and this force is upwards, as we have shown in the diagram. An upward force. All right, so having said that, we proceed and look at the next question. If there are no questions on this particular problem, I don't see any questions on the chat, neither do I see any comments on the Teams platform. So I assume that this suggests that we are good. So this problem continues. The problem continues. What does it say? What does it say? All right, so suppose a 500 kilogram, 900 kilogram car is on the bridge, shown in figure 9.33, with its center of mass halfway between the hinges and the cable attachments. The bridge is supported by the cables and the hinges only. Find the force in the cables. Find the force in the cables. That's part A. Part B says find the direction and the magnitude of the force exerted by the hinges on the bridge. Okay, so assuming that there are two cables in that particular scenario. So what would be the first thing that we do there? So the first thing will be obviously to put a sketch, right? Put a sketch of the situation that we have there. So we can put the diagram. Right, so we have got the weight somewhere here. We've got the car at the center. So this is the weight of the bridge. This is the weight of the car. And here we've got a force going that way. And here we also have got a force at that point. And we're given the angle here is 40 degrees. And here the angle is theta, which is unknown. This is force F. This is tension T. Right, so this will be obviously 4,5. And this is still 7.5, while this is still 1.5. Okay, so this is the sketch that we have. This sketch that we have from this diagram. So this is force F, this is our tension, this is the weight, this is the weight of the car, which is at the center, this is the weight of the bridge. So this is what we have put up here. And we should remember that our torque is equals to R F sine of theta. Okay. And this system, we're told that it is in equilibrium, which suggests that function of the torque should add up to 0. Same applies. Sum of forces in a certain direction should also add up to 0. Okay. So the first thing that we have to do is to calculate or find the force in the cables. Right, so the forces that we have, we've got how many forces there? We've got this one there, we've got 2, we've got 3, these are the forces that we have, and the forces that we don't have is the tension and the force that is in the force F. All right, find the force in the cable. So the force in the cables is basically T, the tension. Yeah, T, the tension. So that is what we're looking for at this particular time. We're looking at the tension. All right, then we'll go ahead in the next part of the question to solve for the magnitude of the force, which is F. So at the moment we're interested in T. So which means if we're interested in T, why not take moments at this point? We're going to take moments at this point, which I've highlighted in green, so that we eliminate this unknown force F. We remain with only one unknown, which is the tension, the weight of the car, and the weight of the bridge. We remain with those 3 unknowns. And this should be sufficient to solve our problem. What do you think? So let's carry on and now do the problem. So we're taking moments about the hinge. Okay. So for the weight, we realize that this at a right angle, so theta is 90. Right, so if we're taking the hinge, this will be an anti-clockwise. This will be anti-clockwise torque. And what does that mean? It means it's going to be positive, right? It's going to be positive. So this is going to be positive, and these two are going to be in a clockwise. So this means they are negative. So what that means that our torque due to the tension will be equals to, sorry, it will be minus the torque due to WC minus the torque WB, which is equals to 0. And which means we can immediately make this subject. This becomes torque due to the tension be equal to weight of the car plus weight of the bridge. And this is going to be, remember, RF sine theta. So our R from there to there, 7.5 plus 1.5, it's 9. So that is going to be 9 T sine theta, which is sine 40, equals to the torque due to the weight of the car, and the distance from there is 4,5 to the pivot, 4,5 times the weight of the car, sine 90, because the angle is 90, plus weight of the bridge, which is this one, and it's 1,5 meters, 1,5 times WB sine 90. So we cancel this, obviously. This goes, this goes. So we remain with 9T sine 40 equals to 4,5. Weight of the car, we're told that is 900, which is 900 times 9.81 plus 1,5 weight of the bridge. What is the weight of the bridge, by the way? Still the same bridge, so it's 2,500. Times 9.81. And we're looking for T, right? So this becomes 4,5, 900 times 9.81 plus 1,5, 2,500 kgs times 9.81 all over 9 sine 40. So that is how we break down. And so basically this was just substitution. If you understood how we formulated this equation and how we then the rest is substitution basically. So what we now have to do there is just to punch and see what do we get. Please let me know if you are following. Right, so we get 13,000. Is the tension in the string, and what are we expected to find? All right. So we basically have got two strings, so we should divide this by 2. So t in each will be equals to 13,226.8 over 2. So basically say this ends divide by 2. We get you 6,613. That is your tension in each. Okay. So that is how we have tackled that problem. That's how we've tackled that problem. Let me know if you've got any questions pertaining to that problem so far. If there are no questions, then we will definitely proceed. I don't see any questions, so we'll proceed. What is the next question looking for? The direction and magnitude of the force exerted by the hinges on the bridge. So now we're looking for force F, the one that we've labeled as F. Okay, we want its magnitude and we also want its direction. Okay, but now if we had the angle theta, we could have taken moments about this point, but now we do not have that. We have two unknowns. We've got the unknown force and we've got the unknown angle. So probably the best way we could do it would be to just want to create more space. So I'm still going to be referring to this diagram. And what we want to do, we want to remind ourselves that this system is in equilibrium. Therefore, the sum of forces in the x or in the horizontal should be equal to the sum of forces in the the sum of forces in the horizontal should add up to 0, and the sum of forces in the vertical should add up to 0 as well. Okay, So we are going to resolve in the horizontal, we formulate an equation. Also resolve in the vertical, we formulate an equation. All right. So sum of forces in the x and which two forces have components in the x? These are the two forces. And that will be F cos of theta, right? And it's positive, right? And minus t cos 40 equals to a 0. Okay. That is our x direction. And number 2, we resolve those vertical, that will be f sine theta plus t sine 40 in the vertical, and we've got these two going down, wb minus wc equals to 0. So those are the two equations that we can manipulate to solve our problem. So I'm going to copy these two equations down, because we're going to need to refer to these equations, or actually manipulate these equations to get what we want. So we said the first equation is what? F cos of theta is equals to t cos 40, and f h of the hinge, right? That is the horizontal. And the second equation, we said, is what? So this is fh in the x, and this will now be f h in the y. Let me just leave this. And f sine theta plus t sine 40 minus weight of the bridge minus weight of the car equals to 0. All right, so this can simplify to f h sine of theta being equals to weight of b plus weight of the car minus t sine 40. So basically this is just subject of formula that we have just performed there. And we know that when we are carrying out or looking for a resultant, we know that resultant R is equals to the summation of forces in the x squared plus summation of forces in the y all squared. So this is the situation that we have on the hinge. I want you to visualize it properly. We're looking for f, which happens to be our resultant, which we want. And this is f h sine of theta if you resolve. And here down here, we'll be having f h cos of theta. So this f what we're looking for is our resultant. So we can just, yeah, we can just leave it as which is this F, which is this R. Okay. So our F, so I think the best thing would be to find numerical values first. Let me remove this so that we substitute first and get numerical values. So this was going to be equals to T cos 40. T cos 40, what was the tension? It's 13,226. So this becomes 13,226 times cos of 40. All right. It will be equals to FH cos 40. I mean cos theta. All right. As you can see that it's equal. Then for this one, weight of the bridge is 2,500 times 9.81 plus weight of the car, which is 900 times 9.81 minus 13,226 sine of 40. So we're going to punch this. So let's start with the horizontal component, which is 13,226.8 cos 40. We'll get a value equals to 101.32.3 newtons. Then the vertical will be 2,500 times 9.81 plus so I'm going to 4,851.98. Okay, and we said to get the resultant F would be the square of the vertical component plus the square of the horizontal component. Okay, it will be F H cos theta squared plus F H sine of theta squared, but the values we already have. Value for FH cos theta is 101.32.3 squared plus 24,851.98 all squared. So we get 26,838.1. The same as 2.7 times 10 to the power of 1, 2, 3, 4. So which is what we are expected to get, right? Which is that. Then obviously again, you are supposed to calculate the angle, you remember. All right, so I will not calculate this. You will satisfy yourself that you get the answer that has been mentioned that you should get. But after you've obtained your vertical component and the horizontal component, to find the resultant or the resultant magnitude will not be a challenge, and to find an angle also will not be a challenge. So basically this is how we're supposed to go about this particular problem in finding the magnitude of the forces that is being exerted by the hinges on the bridge, which is this particular force there. All right, so this is it. I believe that you are following and following well. Right, we have the next question here, which is probably going to be the last question that we're going to look at on the FVV 101 questions. What does it say? What does it say? It says a sandwich board advertising sign is constructed as shown. The sign's mass is 8 kgs. Calculate the tension in the chain assuming no friction between the legs and the sidewalk. And part B, what force is exerted by each side on the hinge? Each side on the hinge. All right, and it seems like the answers are similar. So how do we go about this question? How do we go about this particular question? So we should still remember, for a system in equilibrium, we should still remember this, right? And let's identify the forces that we have on the system. The forces that we have on the system, we've got obviously the weight going straight down, right? We've got the weight going straight down. And we are obviously going to have a reactional force here at this point on this leg. And then this chain is going to experience a tension. And this tension will be in this direction. So we're considering this leg Okay. Okay. So first, that is what we are going to look at in this problem. So the forces that we have identified. Okay. But obviously we realize that there is only one force that is in the horizontal. Okay. So which suggests that there is probably going to be another force that is going to act where by the hinge to support this tension. And obviously the reaction force is equal to the weight. So at least that's what we can start with. And now that we know that there is a force that is at the hinge which we do not know, the hint will then be to take moments at the hinge to eliminate the unknown force at the hinge, which is keeping the system in equilibrium. All right. So how about we do that? So if we take moments at that point, let's identify which force, which turning effects are going to be positive and which one are going to be negative. Right. So taking that hinge to be a pivot, tension T is going to move towards the right there. So which means this is going to probably swing in this direction. And that is anti-clockwise, right? Meaning it's going to be positive. So the torque due to the tension is positive. Then let's see this one also, it's going to be positive, right? Because it's going to put it in this direction. So it's going to plus torque of the weight plus this one will pull it in a clockwise direction. So this will be negative. So this will be torque due to which is close to 0. Ask yourself, what are we looking for? Tension. So you might as well make the torque due to the tension the subject. Okay. Now the next thing would be to recall our formula. We've just been using it. Right, so what do we do next? So we now have to find the distances or the perpendicular distances. Since we don't seem to be having any angles there, we can actually, so for perpendicular distances, right? So this is going to be T times the tension equals to the R, we'll go this R, then multiplied by R minus R due to the weight times the weight. and we are looking for t. So you can make t the subject, t equals to r. So we've considered for theta equals to 90 degrees. And then divided by r tension. So now let's substitute now from this r to the pivot, distance to the pivot. So this is our pivot. That is our pivot. And the perpendicular distance to the pivot, this is the perpendicular distance to the pivot. You can see it's making a nice right angle. So which means this distance, which is our r is equals to, so r is equals to 1.10 over 2. Okay, so which is, let me just calculate that, 1.1 divided by 0.55 times our reaction force. Okay, so our reaction force, since we're considering one of the legs, it's going to be, the total structure has got a mass of 8 kilograms, which means one of the leg, it's half, so that we're going to be 4 kg. So remember, your r is equal to the weight. So one leg, it's 4 kilogram times 9.81. Okay, so now we look for the weight, r to the weight. Right. So here is our weight that we have here, and the perpendicular distance to the pivot. Oops. It's the perpendicular distance to the pivot. So we are now starting from this point to that point. So that is half of, so that is actually RW is equals to 1.10 over 4. So it's actually a quarter of the total distance. So that becomes that over 4, that's 0.275 times the weight, W, which is 4 times 9.81 again. And now we want the R to the tension. Where is our tension T? Okay, so this is our tension, and we said we need the perpendicular, we need the perpendicular distance. So this is the perpendicular distance to the hinge. We've got a right angle, and we've been already given the 0.5, which is the distance. So that becomes 0.50. What remains is for us to punch that. 0.5, 21.582. So which is what we are expected to get, which is 21.6. 21.6. So basically that is how we've solved this problem. So we just use the concept of force times the perpendicular distance to the pivot. I hope you are following well on that. If you've got any questions, please let me know. And what else? What else are we supposed to do there? Part B is asking for what force is exerted by each side on the hinge. On the hinge, right? So we should remember that this system is in equilibrium. F of x is equal to a 0. All right. Means the sum of forces in the x should be equal to a 0. And we are saying there's a force H there, force acting on the hinge, which is a horizontal force. Okay, which should support this. Okay, so what do we have there? We had FH, right? We had FH or FX tension so tension is equals to FH, so tension is equals to, so FH, I mean, because this is what we got for the tension. This is what we got for the tension. But remember that this is just for one side, okay? It's just for one side of the leg. So basically that is what we're supposed to work out there. So I'm going to end here. For the questions on FVV 101, you'll probably have solved the remaining questions in the next coming tutorial, that is tomorrow. In case there are questions of interest that you may have missed, which were presented earlier, please do check on the YouTube channel for the recording. You should be able to find those problems. So now let's solve questions from FVV 101. Let's just take one or two. Check the one that is displayed there, which is looks like a ladder problem. And we solved that one together. So let's look at it. What does it say? So that's question, let me see, what question is this? Okay, question 11. We just solved question 11 and probably question 12. Okay, so it says a uniform beam having a mass of 60 kilograms and a length of 2.8 meters is held in place at its lower end by a pin. Its upper end leans against a vertical frictionless wall as shown in the figure. What is the magnitude of the force the pin exerts on the beam? So that is what we're being asked to find. Right, so let's put the sketch. Now let's add the forces that are indicated. Having a mass, so it's obviously going to be a weight there by the center. What else? We have a reaction force there, always perpendicular to the wall. We'll have a normal force, always perpendicular to the ground. So this is our normal force. Then what are told, what is the maximum force, the pin? Okay. So if there was no friction, this ladder would slide backwards like that. So because of friction, this ladder does not slide, it's balanced, it's in equilibrium. So we've got a frictional force which is going to be opposing that backward movement. All right. So we are then asked to find the force that this pin, so which means that the resultant of these two forces, okay, of the force the pin exerts. So the force due to the pin is going to be equals to n squared plus f squared, fr squared, the friction. Right, so we've just made a good breakdown to that problem. But now let's remember okay, what is the angle here? Okay. Right, so I've just basically put that expression, and let's remember that our torque is going to be equals to that expression, which is r f sine of theta. Okay. And we should remember that the sum of forces in the x, this system is in equilibrium, the sum of forces in the x should add up to a 0, right? Should add up to a 0. And the sum of forces in the y should add up to a 0 since this system is in equilibrium. Okay. Now let's take moments about point P, which is the pin. If we take moments about that point, it will be according to this expression RF sine theta. So that will be the length of the ladder is what, 2.8, right? Okay, well, if we're taking moments about this point, then this is going to be clockwise, so it means it's negative. And this one will pull that down, and this one is going to be anti-clockwise, so it means it's going to be positive. All right, so it's going to be 1.4 and the force is W sine 90 minus 40. Is it sine 90 minus 40, which is sine 50? Let me just check if this math is right. Sine 0.76. And how about sine okay, so it's just the same. It's just the same as cos 40, right? So if you want, you can express it as cos 40. All right, so this is positive minus 2.8 2.8, and the force is R sine 40. Z angles, okay? Z angle there. So this add up to a 0. So the purpose there is for us to find the reaction force, which will then equate to this frictional force. We get that, okay? And this force, the normal force, is equal to this force y, because the sum of forces in the y should add up to 0, and also the sum of forces in the x should add up to a 0. So if we get our reactional force, it means we've obtained our frictional force. If we have our weight, which means we have the normal reaction, then we can then plug in there. So this becomes 2.8 R sine 40 equals to 1.4. The weight is, what's the weight? 60. So it's 60 times 9.81 sine 50. So R will be equals to 1.4. 60 times 9.81 sine of 50 all over 2.8 sine of 40. All right, so let's see how that comes out. It's divided by 2.8. Get 350.4 newtons. Okay, that's your R. And we've said the summation of forces in the X, so since the system is in equilibrium, which means F of R is also equals to 350.4 newtons. Okay, the summation of forces in the X should add up to a 0. Then your N is equals to the weight. So your N is equals to 600 times 9.81. Now we need to get the resultant at this point, which is going to be here. Okay. And we've been doing this. So F at the pin there is going to be equals to the square root of 350 squared plus 60 times 9.8. Okay. Punch that. Okay, so let's see if we, okay, 0.68 kilo. So this is same as 0.68 kilonewtons. So which is what is expected of us. So basically that is how we're supposed to solve that problem. Okay, that's how we're supposed to solve that problem. Any questions? If there are no questions, then probably look at this problem that we have here. Right, so there we are. That'll be the last question that we're going to look at today. So the question is, the diagrams below shows forces applied to a wheel that weighs 20 Newton. The symbol W stands for weight in which diagrams is or are the wheel not in equilibrium? Not in equilibrium, okay? So this is question what? This is question 12. Okay. All right, so not in equilibrium. So for A, so conditions for a system to be in equilibrium, we know that summation of torque should be equals to 0, and the summation of forces should be equal to 0. So summation of forces in the x, summation of forces in the y should be 0. Okay, so let's consider for A. If you look at A, the sum of forces in the y is 0 because we've got 20 newtons going up, 20 newtons going down. So F in the y is 0. And then for the summation of forces in the x, we see they're all in one direction, 10 Newton, 10 Newton going in that direction. So that is definitely going to be 20 Newton. So already this one is out because it's not satisfying this condition, right? So if you want, you can even check the torque and see, but already we'll eliminate it because of the fact that the sum of forces in the x are not adding up to a 0. Okay, then for B, summation of forces in the y direction, okay, 20 up, 20 down, so it's going to be 8 up to a 0. Then summation of forces in the x, all right, so we've got minus 10 plus 10, so we should add to 0 newtons. Okay, then let's do the torque and see. So it's force times perpendicular distance to force times the perpendicular distance to the pivot, right? So what do we have there for B? So for B, this is what we have. If we were to take moments at that point, this will be R, the radius R, and we've got a force going in that direction, another force going in this direction. So this is going to give us a clockwise, so this is going to be a positive. And this one also, it's a clockwise, so it's also giving us a positive. So definitely this is not going to be a 0. It's definitely not going to give us a 0. Why? Because you realize that the diagram is, remember, you should have this, for the system to be in equilibrium, the clockwise moments should be equal to the anti-clockwise moments, but in this case we only have clockwise moments. We only have clockwise moments, so definitely, so it's going to be, what did I say? It's positive, should be negative, right? This is clockwise, so it's negative. Negative. So summation of the torque, excuse me, will be equals to negative 10 times the distance r minus 10r again. So it's going to be equals to what? Negative 20r. So we see that for this reason we will eliminate B. Why? Because the summation of the torque is not adding up to a 0. Then let's check for C. Summation of forces in the y direction, 10 10 going up, so that's 20 down, so it's a 0. Summation of forces in the x, We have nothing in the x, so definitely that's a 0. Then if we were to sketch, this is what we have. And we're going to choose a point, and this is the point pivot, which means we eliminate the weight W. It will not contribute to the turning effect. Right, so this side, it's going to pull up in that direction, so it's going to give us a clockwise moment, so this is going to be negative. This one is pulling up this side, so this is going to be positive. So that becomes what? That becomes negative. Okay. Summation of negative 10 r plus 10 r, which is equals to a 0. So this satisfies both conditions. Satisfied, that is satisfied. So C is in equilibrium. Okay, but this one is asking for which one is not in equilibrium. Okay, so let's check D. So already we have two which are not in equilibrium. We've got A, we've got B. Then let's check for D whether it's going to be in equilibrium or not. So for D, sum of forces in the Y, we've got 10 going up, 10 going down, so it's a 0. Summation of forces in the X, there's nothing, so it's a 0. Let's see if we put that sketch. We've got that. We've got that as well. And we've got the weight. So if we're going to extend this force on the left going down, it'll be an anti-clockwise, so it's going to be positive. The turning effect will be positive. And this one anti-clockwise again, so it's going to be positive. So it shows that summation of the torque is going to be plus 10. So we're multiplying, taking moments about that, about the center of axis. So it'll be 10r plus 10r, so it's going to be 20r. So this condition is not satisfied, doesn't satisfy the conditions for the system to be in equilibrium, which means that only C is in equilibrium. So which means A, B, and D are not in equilibrium. So if you want, you can try out the resultant turning effect of A, which we didn't do. Okay, but already from the sum of forces acting about a system, it's not adding up to a 0, so it suggests that it is not in equilibrium. So any questions? So you should basically remember, if you're dealing with static equilibrium, you need to satisfy two conditions to prove that the system is in equilibrium. Or if the system is in equilibrium, make sure you use both conditions in solving the problem. Resultant torque equals to 0, resultant force equals to 0. And in resultant force, make sure that you are also considering the X component. So the sum of forces in the X component should add up to a 0. The sum of forces in the Y component should also add up to 0. So if you remember that, you will not have a challenge in solving problems that involve static equilibrium. So with this, I leave you here. I wish you the best in your studies. Continue practicing and you'll be good to go.